Okay, so the first thing I'll draw your attention to is that assignment 1 is posted. So you can get started on it. You have 2 weeks to complete it. I won't go through all the details of it. Maybe next week when you've had a chance to review it, you might have more questions about it. But I'll just give you a quick preview. So it's due in 2 weeks at 3 p.m., so before class. And as I mentioned, everyone has available to them one slip day. So a slip day entitles you to hand in an assignment late. You can choose to use it on assignment 1. If you use it on assignment 1, you can't use it on assignment 2. Instead, you can not use it on assignment 1, so you can hand it in on time. Then you might as well use it for assignment 2, because those are the only 2 assignments. If you use your slip day, it gives you an extra couple days, so you can hand it in on the Friday at noon after the assignment is due. Okay. Assignments are submitted digitally, so I want a PDF, no other formats. And you will submit it through a service called EAS. The link is there. The first person to submit, if it doesn't work, send me an email. Sometimes it needs some configuration, but I think I configured it correctly. You'll see it's pretty easy to use. You just put it under assignments and then assignment 1 and upload it. If you say you submit it, you want to change something, still not past the deadline, you can just resubmit and it will write it over top. So don't worry about that. The final thing is that not everyone might have access to EAS. So if you're registered in Gina Cody and you are, like if you have a Gina Cody email and things like that, then the system will work. If you've never logged into any system, the Gina Cody is different than My Concordia. So you have a different username and password. And if you're not in Gina Cody, if you're in, I don't know, John Molson, or maybe you're at a different university or something like that, then it's going to require you to submit a ticket to make sure that you get access to this. So maybe well before the deadline, you can just try and log in to EAS and make sure it works, and then you can resolve any problems. Worst case scenario, you can email it to myself, or even better yet, I won't mark the assignments, so we have a TA for the course, Massa, and her contact information is on the course website as well. Okay, so just very briefly, the topic of the assignment will be vaccine passports. So vaccine passports are something that was introduced recently in Quebec. I try and give you a good capture of what exactly the Quebec model entails. I'd like you to think about this from a security and privacy perspective. What I gave you is also 2 other theoretical systems that Quebec might have chosen to use. So they didn't use either of these 2 systems, but there might be other places in the world that do things kind of like one of these 2 systems. Okay, so you have 3 systems to look at. In the first part of the assignment, you're going to consider Stride on first the Quebec system, and you're going to do it one by one. So you'll look at spoofing. And for spoofing, you'll think, okay, is spoofing even a consideration? Maybe it's not. Maybe there's spoofing has nothing to do with vaccine passports. Okay, so then you can argue, oh, it doesn't apply. But if you think it does apply, then you can say, okay, these are the requirements of the system with regards to spoofing. So this is what it needs to protect against. And then you can state whether the current system does protect against it, or maybe there's some attacks you can think of that just aren't protected against. So you can list one of those 2. Okay, and then you do the next for tampering, repudiation, and each of them. Okay, they should be pretty short. Okay, so I don't want, I want pages and pages. The TA doesn't have time to read a lot of stuff. So try and write like 4 sentences for each of the Stride, and then another 2 about the other 2 systems. So there's 2 other systems, and are they any different, or is it the same? That's basically the question that you have to answer. Okay, so those are each worth a mark. And then in part 2, you'll develop a bit of an evaluation framework. I'm not going to make you do a full-fledged one, but what you'll do is you'll work on the columns. So what I want are 6 security columns. I had this requirement that I was thinking on the walkover, forcing you to choose things using Stride. I think I'm going to drop that, so I'll edit this assignment shortly after class. But You can choose any 6 you want. So try and choose the most 6 important. If they're all spoofing related, it doesn't matter. Whatever you use in question 1, you can absolutely use to inform what you do in question 2, or it could be new stuff. It doesn't matter. But try and pick sort of the most important security criteria that would separate these 3 systems. Okay? Then I want you to think of 6 usability criteria and 6 deployability criteria. Again, for each of them, you have to say, what's the criteria? What does it mean to get a full dot? What does it mean to get no dot? If you want to introduce a half dot, that's fine. Just you can say what the half dot does. And then instead of doing a full chart, what I'll do is I'm just going to get you to evaluate 1 row. Okay? So the row that I'll get you to evaluate is the Quebec system, the current system. And so for that one, you will go through all of your columns and you will give it a dot, a half dot, or no dot for each of your criteria. And then you'll write a quick sentence or 2 saying why it got a full dot, a half dot, or no dot. Okay? All right, any questions about it? All right, so take a look through. You can read it. If these descriptions don't make sense or you feel like there's details missing, things like that, ask me next class. And this is kind of a living document, so I'll update it as people point things out. There's a couple other evaluation frameworks that you might want to look at. Another thing is don't use the password column. Like the point here isn't for you to use the same columns that we came up for the password evaluation, okay? Some of them might apply, so there's no harm in reusing some of them, but the idea is vaccine passports aren't passwords, right? So these are going to have a different set of criteria that's different. Now, because it's kind of authentication, there's actually a fair bit of overlap between the two, but sometimes students have thought in the past years when I've asked these kinds of assignments that they have to use the same criteria, so that's not the point at all, okay? The point is to come up with your own new criteria. And so you can look at these as well for examples of what evaluation frameworks look like in other contexts. So the first one's the password. The second is for secure messaging protocols. This one is for things related to HTTPS, which we've been talking about in class. This one is related to Bitcoin crypto wallets. And this one's related to secure email. 3 of them coincidentally written by me, but anyways. Okay, yeah, and I don't care about what the PDF looks like as long as it's reasonable, it doesn't matter. And yeah, just make sure that you answer everything, like read the assignment and just do what the assignment says. Don't freestyle it. If you miss things, that's how you're going to lose a lot of marks. Okay, any questions? All right. Now, one other thing I'll draw your attention to is there's actually a policy at Concordia. I wasn't aware of it. Actually, I might have heard of it before, but I forgot about it. But we're not allowed to do final exams in the last week of classes. So what we can do is we can either push the exam forward a week, or you can have it during the examination period. And so I decided to push it forward a week. So you'll have your final exam actually the second last day of classes. And then what's the point of coming to the last day of class? There's not going to be any lecture material. The exam is over. So I'll use that class to just take up the answers to the exam. And I will, a lot of you will be deep into your projects. And so I'll also be around. And if you have questions about your project and things like that, then you can ask them. So the last class is technically optional. You can come if you want or not come. I won't necessarily have your marks for the final exam, but I'll at least tell you what the right answers are. And then you can think about how you did. Okay, so any questions about that? Yep. So the date of the final exam is now November 24th. And then December 1st is the last class. And then December 5th are when I would like your final projects. Okay. This will also kind of, if you're taking multiple courses, you're probably going to have a lot of projects and exams. So by having at least one a bit early, hopefully it makes it less congested for you. It means the course, usually the last lecture is kind of like a lightweight lecture because sometimes I don't get through the material fast enough. And so the last lecture is always like not a full lecture. But this year, because we're ending one lecture earlier, the course will actually be shorter by one lecture. So I have to decide. I'm going to try and compress the material and just move through the material a little bit faster so we can keep everything. Or later on, I'll make a decision about cutting out one lecture of the material. Okay, questions about that? Okay, so this is an in-person test. You can bring a cheat sheet, 1 page, and you can write whatever you want on it. I don't care. And yeah, bring a pencil. It will probably be, there'll be a significant component will be multiple choice. And so you will fill it out on a Scantron form. And so they want pencil, they don't want pen. So make sure you bring a pencil. I'll bring a bunch just in case people. It's good to write the rest in pencil as well. Some professors don't like it, I guess, because you can change your answer after somehow, but I'm going to hang on to your exams. And you'll never see your exam without me present once you've written it. So feel free to write in pencil. It's also easier. You can change your answers and things like that. Okay. All right, that's it. Oh yeah, and office hours I had to change last week. You probably got an email about it. Tomorrow they'll go back to normal. So I forgot to update the website, but they'll go back to 1 o'clock tomorrow. Okay, let me make 2 notes to myself. So I'll update the little bit of assignment 1 about the stride in the evaluation framework, and I will update the office hours. Okay, is there any questions from last week? All right, so last week we started looking at TLS or HTTPS, and we said that there were going to be 3 general strategies to attack TLS. The attack that we're trying to do is we're trying to intercept traffic when we're in a man-in-the-middle position. And we can just learn what we can even though we don't know what's going on, right? So we see messages going back and forth. They're encrypted, but you can actually infer quite a bit even if you don't actually try to decrypt them. The second strategy is we can try and break the crypto. That's what we're going to talk about this class. I'm going to give it to you at a very high level. So I'll tell you I'll give you a high level view of what the attacks are, but you have to know a lot about crypto to understand them in detail. There are things that you could look at in your class project if you were really interested in any of them. And then the final attack that we should also cover today or start covering is we're going to change where the tunnel gets pointed. Okay, so we're the adversary, we want to get the tunnel pointed at us. Then we can decrypt everything because it's all coming to us. Okay. The attack tree itself, I won't do it live in class, but the way it will end up looking is something like this. This is penciled in from last class. I might move things around a bit, but anyway. So last time we talked about recovering traffic from external observation. So what can you see if you're outside of the tunnel? So we noted that you can learn the domain that's being visited because DNS queries are not secure, plus the packets need to get routed somewhere. Okay. This maybe I didn't fully emphasize, but we talked a bit about mixed content. We talked about how if JavaScript comes down, it can rewrite the entire page, so you want to make sure it comes over a secure connection. Another idea is if you're the adversary, you can, let's say that someone mixes your library into their web page, then you could change that library and then just change the display of that page, okay? And if you're able to take over a JavaScript library, like say there's one that's really popular, it's on GitHub somehow, I don't know, you spoof the authentication credentials of the maintainer of it, or somehow you get added as a developer and you're able to change the code, then you could change it, you can make it malicious, and then then you can do whatever you want. All the websites that are loading your code, if you're able to change it, then you're able to change the display of the website. You can do things like phone home with the data. So like whatever the user is typing in, you can take a copy of it and send it over to a server. JavaScript is very, very powerful. Okay, so mixed content is dangerous. Then we talked about fingerprinting, using the length and the number of resources that are coming down to the website. You can sort of get a sense of what website someone's on, but this only works on public websites. Okay, it doesn't work on private websites. So the browser, the attacker has to be able to go to that website first, get a fingerprint of what it looks like, or it doesn't have to be first, it can be after, but they have to be able to visit the same website as you to see what the fingerprint looks like so they have something to compare it to. And then the final thing you might do is just kind of store the traffic for later. So maybe later you can do like attack number 1, and then because you've stored all the data, then you at least have a chance of it. Okay. So just because maybe the attacks of type 1, we called it type 2 in class, but the attacks of breaking into the tunnel, maybe there are no attacks today. If you use TLS 1.3, everything's configured correctly on the server. There aren't any known attacks. Okay. That doesn't mean you're secure against attacks of the future. Okay. And your data today could be recorded, and then those attacks of the future could be applied retroactively to your data. Okay, so what we'll do now is, so we talked about this, and now we'll talk about breaking into the tunnel. Okay, so we hinted at this last class, but what protects a tunnel, or what makes it a tunnel, is that both Alice and the server have a shared key. Okay, so they have a cryptographic value. It's kind of like a password, but it's longer, more random. Both of them know it, and no one else in the world knows it. Okay, now there is a whole protocol for how do they get that key, and it turns out it's amazing. But even if you have a public channel where the adversary can listen, you can still establish a secret key. Okay, so there are ways of going back and forth and coming up with a secret key that only you and the person you're talking to knows, even if you're doing it over a public channel where the adversary sees all the messages going back and forth. So you can take a crypto course like 6110 to learn what those protocols look like. If you heard about things like Diffie-Hellman, that's what we're talking about. Okay, so the tunnel. Okay. Now, you might say, well, what if we guess it? Let's say we guess the key. So if you guess the key, then yes, you can decrypt the traffic. You broke it into the tunnel. But this is going to be too large to guess, even for a computer to guess. Even for a supercomputer that runs the lifetime of the universe, it's not going to be able to guess it. Okay. So this basically can't be guessed. Okay, so brute force, exhaustive search, those kinds of things aren't going to work on this, unless there's something wrong with the way it's chosen. All right, so what we can do is, if we can't guess it, we have to steal it. That would be one option. Okay, so the other option is we can break the encryption that uses the key. So maybe we never learn what the key is, but there's some encryption that's being used, and we can break it even without knowledge of the key. And these kinds of attacks are really hard to do because cryptography is very strong. Sometimes you aren't able, you basically are never able to like completely break the crypto. But you might be able to do a partial decryption. So maybe you can decrypt part of the ciphertext without the key. Or another way to break the encryption is you can do what's called a downgrade attack, which is basically get them to use crypto, get the server and the client to use crypto that was developed in the 1990s that you can break. Okay, so get them not to use the current versions. And TLS, for backwards compatibility reasons, often supports old versions. And the weakest encryption that it supports is actually no encryption. So in early versions of TLS, there's actually an option where you're like, I'm not going to encrypt at all. Okay, and then there's some other ones that are very weak, and you can actually guess the key. So they use a key that in the 90s you couldn't guess, but now with today's computing resources you could guess. All right, so we'll consider these each kind of in turn. All right, so the first thing we'll talk about is key theft. So how could you steal a key? And what I want to do is I'll tell you a story about a bug that existed. I wish I wrote the date down. I can't remember when exactly it was, but it was many years ago, like, I don't know, maybe 10 years ago now, maybe a little bit less. And it was big news when it happened. So like you would like turn on CBC News and they were talking about Heartbleed on CBC News or whatever. Like it wasn't some obscure bug. Okay, it was like a big high profile kind of bug. It broke a lot of the internet security properties, including HTTPS. We'll talk a little bit. And it also had to do with SSL in a kind of indirect way as well. Okay, so what is Heartbleed? So Heartbleed was a bug. It was a software implementation error. Okay. And it was on servers. Okay, so it's not on the clients, but it's on the websites that are serving up websites that are over HTTPS. Okay, so servers today run on a bunch of different operating systems, but one of the most popular operating system is an open source version of Linux called Apache. And so this was a bug that basically was on Apache. And by default, if you install it and you're like, hey, I want to use SSL, they'll be like, okay, no problem. Here's a library to do it. They give you a library. It's called OpenSSL. OpenSSL is like one of the oldest crypto libraries yeah, it's been around for a long time. The person who developed it actually, I think the quote from them is that they wanted to learn C and they didn't know the language C, so they like decided to implement a crypto library just so they could teach themselves C. So it didn't necessarily start on solid ground. Since this bug, but even before and after, people have looked really hard at this library. So this library now is like one of the most hardened crypto libraries that you can find. But anyways, it turns out that in this story, there was a bug in OpenSSL. It was in this like really obscure part of the protocol that almost no one knew existed or had ever looked at. And it had to do with this service called a heartbeat, which is where the name of the attack comes from. All right, so this was sort of turned on by default, but not used. So it was just one of those things that was very early in the protocol. Someone put some code in to offer this service, and it was on by default. Most people, when they look at it, they're really worried about the crypto being right, so they aren't looking at all these other like different aspects, and so it just kind of escaped attention for a long time. Okay. All right, so this stack, by the way, was quite popular. I forget, I don't have statistics, but I think it was something like 40% of servers, and maybe as high as 60% of servers had a stack that looked something like this. Okay, so it wasn't like a corner case that didn't apply. It applied to lots and lots of servers on the internet. Okay, so this is the heartbeat protocol in a nutshell, very simplified, but we'll just talk at a high level. So you have a user, and then you have a server, and the server is running this stack. Okay, so they have this OpenSSL heartbeat kind of stack that they're running. That's just heartbeat OpenSSL Apache. Okay, and so what the heartbeat did, the original idea was, hey, I wonder if this server is actually like listening or not. Okay, so I could just like try to connect over HTTPS, but maybe I'm getting some error messages or something like that, and maybe it's too expensive. So there should be a simple way to just kind of ping in and say, hey, are you there? And then it will say, okay. Okay, so that's basically the idea of what the heartbeat protocol was. And so the way it worked is you would send some bytes to it. So let's say you said A, B, C, D, E, F, and then it would reply with whatever you sent. It would just echo it back. Okay, then people decided that, or developers decided that maybe it's kind of wasteful. I don't know what the logic was, but maybe it's kind of wasteful for them to reply with everything. So what if you let them truncate the response? So instead of sending all the bytes back, you could say, hey, just send me like the first 3 bytes back, okay? So you would add an argument like 3, and then instead of it replying with ABC, it would, or sorry, with ABC, D, E, F, it would just reply with ABC. Okay, then instead of 3, you could do 1, for example, and then it would just reply with A. All right, everyone understand? Okay, so what if you did this instead? So he said, hey, I just sent you a message, A, B, C, D, E, F. Send me the first 10 bytes of that back. Okay. So first off, it should throw an error, right? Because there aren't 10 characters that you sent, or 10 bytes, right? You just sent 6 of them, right? So you shouldn't be able to ask for 10 back. And so it turned out that this was not implemented correctly. And so it would return 10 characters of something back. And so basically what happens is when you send A, B, C, D, F to the server, it has to store it somewhere. Okay, it's processing, it's doing something with it, it's got to put it somewhere. So it puts it in RAM. So somewhere in RAM, there's going to be this string. Okay, and then there's going to be a bunch of other stuff that just happens to be in RAM. Before or after it. Okay, and so when you ask for 10, what it will do is it will actually give you 10. So it will give you it will say, okay, here's A, B, C, that's 4, 5, 6, 7, 8, 9, 10. Okay, so it will give you whatever else happens to be beside it in RAM. So this is called a buffer underrun. And what's the limit? So you can ask for 10 hex characters, like how much data can you get? And so the buffer basically allowed you to get 64 kilobytes of data. Okay, now the other thing, just a small detail, is that this information is stored in a stack. Doesn't matter, but basically if you overrun the buffer, or underrun in this case, the stuff that you get is the stuff that you had before. So you're not, like here it looks like I put this information in, then I put this information in, and then these X's are stuff that came in after. It's the opposite in a stack. So this is put at the top of the stack, and when you underrun it, you're going to get the stuff that was before it. That's why it's called an underrun instead of an overflow, which is a similar kind of thing. But basically, you're going to get data from the server's memory. And it's basically going to be things in memory from before you running. From your call to the heartbeat. Okay, so now next question. What's the kind of things that might be in the server's memory? Okay, this is a website. It's got RAM. It's got a bunch of stuff in its memory. What is it? Is it just like system configuration junk? Is it a bunch of gibberish? Is it a bunch of encrypted data? Like what exactly would be sitting there?
Keys, passwords, emails.
And how would keys, emails, and passwords end up in RAM?
Okay, so when we send our data, like username and password to the server, it will be processed in the memory. So yeah.
Okay. So basically all the encrypted data that the server is returning, it needs to decrypt it to look at it. Okay. It's going to put it in RAM, right? Then it's going to decrypt it into plain text in RAM, using a key that's also in RAM. Okay. So the kinds of stuff that could be sitting in RAM beside your heartbeat message are any kind of sensitive information that the website would have gotten recently, like from the other users that connected just before you. Okay, so it's going to be other users' stuff. So it could be their passwords, it could be their cookies, it could be their like data, like whatever they're submitting, text that they're submitting, files, anything like that. Okay. And it's in plain text. Okay, so it could be in both ciphertext and plain text, but that decryption happens in RAM, so the plain text gets written back to RAM. Okay. All right, so this is a way to break into the tunnels of others because you can see their information sitting beside your request to the server. Now, the other thing that you could do, and it was speculated that you probably couldn't do this because you could only return 64K. The server's RAM is going to fill up really fast, right? It's online for an hour and it's full and it's like recycling the RAM and things like that. But there's one thing that has to exist in RAM, which is the session key that's being used to decrypt everything, okay? And not just the session key, but there's a long-term key that's used to create the session key. So that it's kind of complicated with the crypto, but basically there's this like long-term secret, and if you can capture that, then you can actually like fully impersonate the website, okay? Now that long-term key is like the first thing that OpenSSL is going to put into memory. It's like the first thing that you need. So you put it there, then people start connecting to you, and then your RAM, like the stack fills up with lots of other junk, right? So people thought, well, theoretically you could get that key out, but by the time you come around to a server, it's already been online for so long that it's so deeply buried that you'll never reach it because you can only reach 64K of the most recent data. So that was the speculation. And I think it was Cloudflare that actually said, they wrote a blog post about like why this attack wasn't possible. So then someone decided to prove them wrong. And so what they did is they found a way to force the server to restart. Okay, so they found an exploit. It caused the server to restart, and then they hit it right away as it rebooted, and they were able to extract the long-term cryptographic keys. So you can also find the session keys, which are kind of like these temporary keys, and even like long-term crypto keys. If fast enough. Okay, in Canada, an example of a website that was exploited was CRA, so the Canada Revenue Agency. The person that did it got caught, and they actually were criminally charged. And I forget if they went to jail or what the sentence was, but they were found guilty for data breach for it. So it was a kind of high-profile issue. And it was something that even if you're like, if you read about the attack earlier and you were curious, so like what other websites could I find this data for, you absolutely shouldn't do that. Okay, so if you ever hear about attacks, you shouldn't just go out and try it because you're curious, because it could lead to criminal charges. It's illegal. So yeah. Okay, any questions about this bug? Okay, here's another way of stealing keys.
How was it patched?
Oh yeah, so they basically disabled Heartbeat. No one used it anyway, and they pushed out an emergency update, and so yeah, people installed it within a matter of hours, days, depending on how active they were. And so now I think there's very few servers that are vulnerable to this issue left on the internet. Most of the major services were patched within a couple days. It might also be the case that the people that discovered it, I think they probably disclosed it. So you probably heard of responsible disclosure, where basically you go and if you found this bug, you would go to OpenSSL and say, hey, here's a problem. Give them some amount of time, like maybe 3 months, 6 months, something like that, to fix it before you go public with it. And then maybe they would also reach out to the major vendors and get them to update. Of course, once people start updating, then you can kind of see it, and there's a chance that it gets leaked. And so anyway, the way that you choose to reveal bugs if you find them, that's like, it's a contentious issue. Different people have different opinions on it, but you should consider the ethical implications of what you're doing. So, yeah. Okay, this one I won't talk a bit about. I just want to put it on your radar. There's something called side channel analysis. And the one that sort of worked against HTTPS were timing attacks. So what you would do is basically you would tell a website, hey, I want to do HTTPS, and then they would respond to you. And before they could respond, they have to use their cryptographic key. So they have to construct some cryptographic material to send it to you. And if you're really close to them, and you ping them a lot, like you're pinging them, you're asking for 1 million connections or something like that, you can kind of figure out the average time it takes them to respond. And then you can change your request to force them to use their key on different data. And anyways, if the crypto isn't implemented perfectly correct, it may take longer or shorter amounts of period depending on what you're doing. So I'm talking very vague, so let's be very concrete. One thing it might do is sign some data, and it might use an algorithm like the RSA signature algorithm, okay? And so if you ask for a message A, it might take a certain amount of time to sign. And if you ask for a message B to be signed, it might take a slightly different amount of time. And the differences in time depend on their key. So depending on whether the 5th byte of their key is a 1 or a 0, then it might take longer or not so long to sign. And so anyways, if you have a lot of data, you're really close, you have a clean network, their crypto is implemented with, so that depending on what values of the key they have, certain operations take more or less time. If all of those conditions hold, you could actually leak a private key off of a server. So this worked in like the 90s. Then a lot of work went into OpenSSL to make all the crypto constant time. So it doesn't matter what key you use, it always takes the same amount of time. And if there's some shortcut that you can take because you have a bunch of zeros in your key, then you don't take that shortcut in the code. You spend the same amount of time, basically. So OpenSSL is now very hardened against these kinds of attacks, but they still are possible. There's some weird things when you pad data, and the padding can spill into like extra blocks. And anyways, if you take a crypto course, there's a lot of like fine print. And so there are some recent examples of this kind of attack, but they're highly theoretical in the sense that you need a really like perfect laboratory setting because the timing differences are so small. But anyways, this is the kind of thing that you might be able to do. Of course, if you get physical access to the server, say you can't like log into the server, because it's you don't have a password or something like that, but you're able to like measure the power that it's consuming or things like that, then there's other ways of doing side channel analysis attacks as well. So side channels basically, all the kind of weird ways you might look at an implementation of how crypto is being done and infer what the key is, as opposed to attacking the data itself. Okay, another idea is we mentioned downgrade attacks. Okay, so the way HTTPS works is it offers actually a whole bunch of different crypto algorithms that you can use. Okay, so there's a whole bunch of different key exchange algorithms, and there's a bunch of different block ciphers and stream ciphers and blah 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 blah. There's a bunch of crypto that you can use, and some of them are from old versions of TLS, and websites want to be backwards compatible, so they still have old versions of stuff. And when you connect to a website for the first time, you're going to negotiate what crypto you want to use. Okay, so basically your computer is going to say, "Hi, I support TLS version 1.3, and my preferred, crypto." I should actually state this the other way. It's usually the server that initiates it. But so the server will say, "Okay, I support TLS 1.3, and my preferred encryption algorithm is AES 256 in GCM mode, using Diffie-Hellman with ECDSA or whatever." Okay, so like a bunch of garbly goop about crypto. Okay, so that's its preferred algorithm, and it will have a list. And then your client will say, "Okay, yeah, I support that," or "No, I don't support that, but I do support this." Okay, and so you go back and forth. Now remember, you're doing this negotiation in order to create that secure tunnel. So this negotiation is happening before there's a secure tunnel. So if there's an adversary in the middle, they can change your messages as you're negotiating them. So you might say, "Yeah, I support TLS 1.3. The adversary could change that to, "I don't support TLS 1.3. I only support SSL 3.0, which is one of the earliest versions," right? Then the server will receive that message. It will think, "Oh, they support SSL 3.0. Okay, I'll send them the old crypto." Okay, so that's the idea of a downgrade attack. Now, for reasons that are sort of maybe too complicated to really worry about, TLS, in its original vision, it got really lucky because it didn't let you negotiate everything about the algorithm. And one thing it didn't let you negotiate is the way that you ensure that messages aren't modified. Okay, so this is using something called max, and it would not allow you to negotiate that point. The new version actually does, but anyway, the old version wouldn't let you. So the way to prevent downgrade attacks that actually works is you have this conversation, you establish your key, and the server and the client don't trust the key yet because they know that there's an adversary that could have changed the negotiation, okay? But once they have the key, then they can use it to sign. I'll use the word sign. It's actually apply a MAC, but it's kind of like a signature. They can sign what the previous messages that they were that sent, okay? So basically, I'll say, I want to do TLS 1.3. The adversary will change it to 3.0. The server will hear 3.0. They'll send me a response. We'll end up with a key. And then I'm going to say, "Hey, now that we have a key, by the way, I told you that I want to do TLS 1.3. Is that what you heard?" And the server will say, "Oh, no, I heard that you want to do 3.0. And then I'll say, "Okay, tear down this connection and let's start again." Okay? Because those keys, the keys that apply to the integrity of the thing couldn't be negotiated, and they were secure even from the early versions, that countermeasure worked against downgrade attacks. Okay, but what you could do is you could work on downgrading the confidentiality. Okay, so the confidentiality, how secret the data is, those kinds of algorithms were negotiable, and there are some older ones that have no encryption or have super short keys, not super short, but short enough that they could be brute forced even with like a MacBook Air. Okay, so anyways, in order to do these downgrade attacks, it's not enough to it's not simple. It's not like you just drop in the middle and downgrade. You have to like come up with some exploit, or there has to be some implementation error or something like that that allows you to downgrade, okay? And so anyway, there are lots of versions of downgrade attacks. They're kind of complicated. They mix some stuff about crypto with stuff about implementations, and you can read about them for your projects if you're interested in. But I won't say much more about it. I just want to give you kind of the high level picture. So the key idea is that the crypto in HTTPS can be negotiated, or is negotiated. And an adversary might be able to get you to use an old version. So there was one recent example of an attack like this. It's called Freak. So that's just a pointer. If you're interested about it, you can read more about it. Another thing I'll mention here too is that what's the worst crypto that's in SSL or TLS? It turns out that when SSL was added to browsers in the United States, so the main browser at the time there was Netscape Navigator. They're the ones that developed TLS, SSL. And there was Microsoft Explorer that came shortly after. Both of these are American companies. So Netscape and Microsoft are American. Because they're American, they're subject to American law. Okay? And American law at the time actually treated cryptography as if it was a weapon. So cryptography back then was something that the military used. And they had laws that said you can't export a cryptographic algorithm to certain countries in the world. Okay, if you export it, it's like sending them a bomb to them, like exporting like some weapons or something like that. Okay, that was the law at the time. Now, Netscape and Microsoft were fighting the law, and there was a lot of crypto enthusiasts and stuff saying, no, like we need this for privacy. It also makes the internet secure. You know, you can do secure banking transactions and things like that. Like cryptography shouldn't just be for military use only. Okay, but that was the letter of the law. So then what the browsers did is they offered a weak version. It was only 40 bits, if that means anything to you, of encryption. And it was put into every version of the browser. And the idea was that if you were in the US and you signed the terms of agreement in the US, you could use strong crypto. And if you were anywhere else in the world, you would use the weak crypto. Okay? But they somehow messed up when they rolled out the browser, and they made it so that everyone used weak crypto. Okay, so they didn't even have the option like to use the strong crypto, even though it was there. But anyways, the protocol supports this weak 40-bit encryption. The laws then changed. So Bill Clinton in the 90s became president. He changed the laws and made crypto legal and things like that. And then all the browsers updated with strong crypto. Okay, but because libraries want to be backwards compatible, even with systems that are like from the early 90s, they still had this option for these weak. They're called export ciphers because you could export them. They're 40 bits long. And so that's what Freak did, is it looked at some implementations of SSL libraries, and it found a sort of exploit path to force a negotiation where people were using these old export ciphers, even though the software was modern. They were using a modern version of it. But because they were still there, they were still an option, and there was a complicated way of doing a downgrade attack, they were able to do it. Okay. Okay. Now the next type of thing you could do is you could attack the crypto. So you could try to recover plain text. Sorry. Okay. So the first, or I'm just going to give you the really high level flavor of this attack again. There were some versions of SSL that use compression in conjunction with SSL. So basically when you sent data back and forth, you weren't just encrypting it. Before you encrypted it, you first compressed it. This was more common when you were talking over UDP as opposed to TCP. So it wasn't for like if you were downloading websites, HTML websites, which come to you over HTTP, which come to you over TCP. It was when you were, say, on Netflix, you're watching video, maybe they have encryption turned on, they're streaming it to you. If you drop packets, it doesn't matter. By the time you figure out that they were dropped, you can't, like the video has moved on from that point, so you don't care. So that uses UDP. There is a version of TLS that uses UDP, and that's where compression might be deployed. There was also some experimental replacements for HTTPS that use compression. There's a protocol called, what was it called? Can't even remember now, but anyways, Twitter and Facebook ran it, and I think Google, the three of them, and they experimented for a while, but they've kind of discontinued it and moved on from it. But anyways, okay, so the basic idea, high-level idea is this. You have a user, and this is like a complicated attack. It's not like something that's just going to work out of the box on a lot of different encryption algorithms. But the user is on some sort of website. Okay, and there's some content on the website. It doesn't have to be a website. Like I said, this generally didn't actually apply to websites themselves, but I'll illustrate in terms of website because it's easier to understand. So there's some content that the adversary controls. Okay, so think of it as like an ad. So the user's on a website, and there's some ad on the website, and the adversary is actually controlling it. So they don't control the whole website, but they control what's inside that advertisement. Okay. All right. We're going to talk about cookies later when we talk about policies, but think of it this way. So let's say you're going to a website, and it's the kind of website where you log in, so like Google, Facebook, more Facebook than Google, Twitter, that kind of thing. Twitter. Maybe this is a tweet that's in your timeline or something like that. Okay, so there's some website, and you normally would log in. So the way you log in is you type in your username password, so that's fine. You hit enter. The server takes it. They compare it to that list of hashed passwords, hopefully salted and hashed a million times, and they say, okay, this is the same. This is the right user. Okay. Now you get redirected. And now you start browsing your timeline. So you click on tweets and things like that. Do you have to put your password in every single time you click within Twitter? You don't. Okay, so somehow it remembers that it's still you. Okay, so you log in once, and then you stay stuck logged in, for as you use the website. Then maybe when you close the browser or not, depending on the website policy, you might have to log in again. Okay. So how does it know that you're the same user that keeps coming back? Because there's a million people that are connected to Twitter, every second. And so they're getting lots of requests. And so how does it know that, oh, you actually are you? Okay, so one thing you could do is record the IP address. Now the problem with that is you could spoof the IP address. So if I want to be you, I wait for you to log in, and then I start sending messages from your IP address, and then they come back to me, and I'm logged in as you. Okay, so that's not good enough. Okay, so cookies are the answer. But that's a word. What is it and how does it work?
When you log in, the code, they recognize by the code.
Okay. So basically a short end, I'll explain cookies in more detail later, but what the website is going to say, okay, you logged in, that's good. I'm going to give you a number, like a unique number that represents you. It's going to be a secret. Okay, you can think of it as a session ID or something like that. So it's a secret number. And your browser is programmed to accept and store these numbers. Okay? So it's not just something that's happening within the website itself. It's something that's happening at the browser level. Okay? So cookies are supported by the browser. And so what happens is your browser then stores this cookie for that website. So we'll say twitter.com and this cookie value. Now, every time you go back to Twitter and send some packet to it, what your browser does is it looks through its list of cookies, which are in a cookie jar, and it says, do I have any cookies for twitter.com? and it sees, oh yeah, I have this cookie, it throws it into the header of the packet and then sends it off to Twitter. Okay, so it staples these cookies in. So then when Twitter receives the message, it says, oh, here's this ID. It's a secret. Remember, this is all happening over SSL. And so it's a secret number. And I know that this number represents Jeremy Clark. And so I'm going to assume that he's still logged in and it's still him that's talking. Okay. So basically, if I go back to Twitter after I've logged in over HTTPS, basically I send some request to Twitter, like give me this web page or give me this image or whatever, and my browser is going to stick my cookie into the request itself. Okay. And then I'll get a response back. Okay. Now, the next thing is the adversary. So before, actually, I was a little wrong. I said that maybe it would be an ad. That was kind of a wrong mental model. It needs to be a little more powerful than an ad. It needs to be like JavaScript or some active scripting resource. Is a question? Yeah.
Can't they use the cookie of someone else, like IP address?
Okay, so let's say, what stops me from stealing your cookie? So let's say that, first, to answer your question, let's say I can steal your cookie. Does that mean I can impersonate her for the whole web? So it does mean that. So stealing your cookie is basically equivalent to stealing your password. The only difference is that the cookie will eventually expire and your password will probably live longer. So I'd rather have your password than your cookie. But if I'm able to steal your cookie, then it's as good as being you, at least for that time period. So we call that session hijacking. So if I can steal your cookie, then I've session hijacked you. So what stops me from stealing your cookie? The answer is it's not based on your IP address or anything about you. So it's going to be some number that the server chooses that's completely random. So it's going to be kind of like a cryptographic key in that sense. Okay, so it should be too long to guess. So I can't try every cookie value. And it should be randomly chosen by the server. And then the second component is that all this conversation happens over HTTPS. Okay, so this is secure. This is a secure tunnel. So if I'm looking at the tunnel from the outside, I just see the ciphertext. I see an encryption of your cookie go across, but I don't have a way to decrypt it and steal your cookie. Okay. Now, what happens if this doesn't happen over SSL or HTTPS? Okay, if it doesn't happen over HTTPS, then I can just steal your cookie, right? And so what happened, once again, it was maybe 10 years, all my stories are 10 years old, I apologize. But all your major websites, Twitter, Facebook, those kinds of things, they didn't use HTTPS always. Usually what they would do is they would use it to log in. So you would send your password over HTTPS so someone couldn't lift your password out. But then once you sent your password, they would redirect you back to HTTP. And so you would be sending your cookies over in plain text. Okay? And people theoretically knew that that means I could steal your session. If I was able to get in between you and Twitter, I could pull that cookie out and then I could impersonate you. Okay? But you know, it's kind of complicated. How am I going to get myself in between you, right? And like, am I smart enough to like write the code to like steal your cookie and then log you in automatically? And like, yeah, sure, it's theoretically possible, and maybe like an elite hacker could do it, but it's not like, it's like, who cares? That was sort of the attitude. Then what someone did is they came up with a Firefox extension called Firesheep. And Firesheep was like a super simple interface. What you would do is you would go to a Wi-Fi network, and what it would do is it would first get it so that it was sort of impersonating the gateway of the Wi-Fi address, so of the router. So everyone else that, like, say you go into Starbucks, you could do this. You could go in, and everyone who is on that Wi-Fi router, on that Wi-Fi network, started routing their packets through you. Okay, so it was able to get you in the middle, and then because there was no HTTPS, it would just pull out the session ID. And then they made such a good user interface that basically you would just log into Starbucks, you would open up the extension, and then it'd be like, bing, like Jeremy Clark's online, bing, this other person's online, bing. And then you just double click their name, and then you'd be logged in as them. You'd be on their Facebook homepage, like looking at it. And so anyways, it was so simple to use. Then everyone freaked out. And that was like one of the main drivers of pushing servers to HTTPS. So at that time, everyone switched to using HTTPS all the time, not just for logins, because that attack, it wasn't that someone found the attack, it's because they took the attack and they made it simple, right? So anyways. Okay, back to this. All right, so what would happen in this case is, remember they're using compression. Okay, so first what would happen is if the adversary is able to run JavaScript, they can actually they can control basically this request. Okay, so the adversary can control, JavaScript is powerful enough that you can ask for things. Okay, so you can basically ask for whatever you want from the web server. You can open up a connection. And so the adversary was able to create a request of their choosing. Okay, so they could choose this value. And the browser would attach the user's cookie to it and send it. Now, the JavaScript couldn't read the cookie. So the cookie was added after by the browser. Okay, so just because you controlled JavaScript, you couldn't grab the cookie directly. Okay, but what you could do is you could guess at what the cookie value was. Okay, and so what you would do is they would send requests like this. They would say, okay, I know that, well, whatever. I'm going to guess like A. Then your cookie is going to get prepended to it, and it will get sent across. Okay? And when it gets sent across, it first gets compressed. Okay, so there's like a smaller version of this packet. And then this is what gets sent across. And if I'm an adversary, I'm also sitting on these wires. And so I can see the size of the packet as it goes across, after it's compressed. Okay? Now, let's say that your cookie contained the value AAAA. Okay? Would that compress well or not well? Why would it compress well? Okay, so compression works when you have repeated data. So if you have data that's repeated lots of different times, like say you have 1,000 A's in a row, right? Instead of sending 1,000 A's, I can just say, take the letter A and write it out 1,000 times. So that's a much shorter message than A, okay? So when you have redundancy in the data, that's when things compress well. If you have data, it's really random and like there's no patterns or redundancies or things like that, then it doesn't compress so well, okay? So if this guess is right, basically what I'm going to do is I'm going to guess, and I don't have to guess your cookie all at once. I can guess pieces of it, because remember, it's too long to guess all at once, okay? But if I have a good guess, so this is a guess, and if it's a good match to your cookie, then it will compress well. And I can see that it compresses well because I can see the size of the packet as it goes across the wire. Okay? If my guess is completely wrong, like you don't have that anywhere in your cookie, then it's a bad match. And then it's not going to compress at all. Okay? It's going to not compress. Or not. It's barely going to compress or not at all. Okay, and once again, I can see whether it compressed well or not. Okay, now I have to do this a lot. Like I have to do it 100,000 times or something like that. Okay, so you have to stay on the website long enough for me to do it. And so there's a lot of like kind of red tape. It's kind of a theoretical attack. But I can do this enough that I can start guessing pieces of your cookie, and eventually I will be able to guess it all. And even if you navigate away from the website before I'm able to completely guess it, I've narrowed your cookie value down. Okay, so I now know I know more about your cookie than it's just a completely random thing. And then maybe I can do like an exhaustive search after I do that. Okay, so this is an example where you're not going to first off, it's a very elaborate setup. You know, the adversary has JavaScript, plus they're on the line, they're watching it, plus they send hundreds of thousands of requests, blah, 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 blah. So it's not a very realistic attack to begin with. But secondly, you are only able to recover a small value, okay? You're not going to recover like 100 emails from someone's message, because you're only going to be able to guess things a couple bytes at a time, okay? So it's going to be an attack that's really hard to do to decrypt everything that's going over SSL. But if there's some small value that's really critical, and you're able to just decrypt that one little bit of the message, then that can do a lot of damage as well, okay? So the lesson here from the TLS or HTTPS perspective is it's important to your encryption has to cover every byte, right? Like not every byte is equally important, okay? But there are some bytes, and there are not a lot of them, that are really, really critical, okay? So you need your protocol to not just allow people to stop people from decrypting everything wholesale, but they have to not even be able to get partial information about partial target bytes, okay? So anyway, there's a bunch of variants on this style of attack. So this one was called Crime. They all have like kind of acronym kind of names. And then there's other kind of variants that use different aspects of crypto to, so the first one actually before Crime was Beast, but it's a little more complicated to explain. So that's why I try and use Beast. There's Lucky 13 that combined this kind of attack with a timing attack. There's a stream cipher called RC4 that used to be supported, and certain bits could be guessed. You couldn't guess all of them, but you could guess some of the bits. And so you try and slide the cookie into the bits that you could guess, and then you kind of move. You would guess a bit of it, and then you kind of move it around, and then you were able to guess the whole thing. There's another one called Poodle. I forget the details of it. So once again, not expecting you to know all the details of these, but they're just more for interest, but try and understand the sort of high level concept. Okay, so if we go back to our tree, this isn't a mistake. GoToFail actually is somewhere else in the tree. I'm going to get rid of it. But you can see there's attacks on the protocol or on the implementation. So Beast, RC4 biases, Poodle, Crime, they're attacking how SSL is done. And then you can attack the implementation. So Lucky 13 is kind of a combination. It both attacks the protocol, and it also uses timing as a side channel. There was downgrade attacks like Freak, and then there's Heartbleed to extract the private key. Okay, so that's it for this part of the tree. So we've talked about all of this stuff. And last class, we talked about all of this stuff. Now what we're going to do is we're going to talk about the last category, which is actually the biggest, which is how do you get that tunnel pointed at you? Okay, so we'll do that, but let's take a break first. So it's 10 to 7, so come back at 7:05, and we'll start again. Okay, now we're going to talk about the third kind of attack on SSL or HTTPS. And that is, we want to get the tunnel pointed at us. Or a more technical way of saying it is we're going to subvert server authentication. All right, so from your perspective, here's Alice, and she uses HTTPS. And her browser knows that it just created a tunnel. It can see the end of the tunnel, and it can see that it's putting its data into the tunnel. But the question is, where does the tunnel end? Okay, so what's the end point? So if that tunnel ends before it even leaves her computer, that means everyone can see it from then on, right? Maybe it ends at her Wi-Fi router, right? Then everyone can see it. That's further down the line. Maybe it ends in the middle of the internet somewhere on a server, okay? Maybe it goes all the way to Twitter or Facebook or Google, okay? That's what she wants, all right? So how does her computer, how does your browser figure out where the tunnel ends? If it doesn't end in the right place, then it's basically useless to use a tunnel at all. Okay? So a tunnel is only useful if you know that it actually is ending where it's supposed to. Okay? So if you can control where it ends, it's a completely devastating attack. Like it just, you might as well not even use encryption at all. Okay? All right, so the endpoint of a tunnel is basically a number, okay? And it comes from cryptography. It's a number. It's called a public key. Okay, so when you set up the tunnel, you say, this is the public key of where I want it to end. Okay, and that's all you need to know about crypto, really. So a public key is like this key. Someone controls it, and specifically, they control the corresponding private key. So there's a key pair where one's public and one's secret, and the entity that controls the secret key that corresponds to the public key is the only one that can do anything with the data that's coming out of that tunnel. Okay, so you might as well just think of it as the tunnel ends at them. Okay. All right, so entity that controls the secret key that corresponds to the public key is the endpoint of the tunnel. Okay. All right, so now let's just forget about cryptography. Okay. A public key is a number. All right. So all I need to know is if I want to connect to Google and I want to know that I'm actually talking to Google, is I just got to make sure that that number is right. So Google has some number that's their public key. And as long as I get Google's real number, then I'll form a tunnel to Google. Okay? Or at least if the tunnel goes somewhere else, no one can do anything with the data. Okay? So this whole problem can basically be like reduced to, if there's a directory somewhere that's like, here's Google, here's their number, here's Twitter, here's their public key, here's Facebook, here's their public key, right? If I have that, then it's done. Okay? Then I can form a secure tunnel to them. There's no attacks that are possible or anything like that. Okay? Now, the question is, is there such a table? Is there like a table where I can look up what everyone's public key is? And if not, then how does my computer figure out that, oh, this is the right number for Google? Does anyone know the answer? Okay, so this has to do with certificates. Okay, so what's a certificate? A certificate is just a document, like it's just a bunch of data. Think of it as like a text file. And you can put whatever information you want in it. So you might say there's a website, it's called the subject or subject name. Say it's google.com. And here's its public key. Whatever it is. Okay, so someone wants to put a signature on this. Why do we need a signature? Why can't we just, I go to Google and they send me this file that says, okay, if there's an adversary in the middle, they can just switch it. Okay, and it's important, I didn't say it maybe explicitly, but you need to know this before you make the tunnel, okay? So the tunnel ends at a public key. You got to know that you can't get the public key over the tunnel. Okay, you can't have a tunnel already. Then you don't need the public key anymore because you already have the tunnel. Okay, so you got to get this public key somehow before the tunnel is even made. Okay. So let me actually add that as an explicit point. Okay, so in order to make sure, so the adversary, let's say this is Google's correct public key, and this is in a document, okay? If we send this document around, then the adversary could change it with their own public key. Okay, what if the adversary puts their own public key into this document and you believe it, then your tunnel will end at the adversary and not at Google, okay? So the adversary's goal basically is to, they basically want to replace this number with their own key. Okay, so we're not going to let this just fly around without some sort of authentication on it. So we're going to sign it using a digital signature. So a digital signature is just an algorithm that signs something. And it's going to be signed by a party that we call a certificate authority. So it's some special party that just goes around making sure that these values are right. All right. Okay, so that's it. Now you can put other information in a certificate. So often it might include that, oh, this is Google at Mountain View, California. Okay. Sometimes it will just say this is the server that answers to requests sent to google.ca. We don't know if this is the real Google or not. We're just here to say that it's the right server, and we'll talk in excruciating detail about the differences between them because they're meaningful. But anyway, so you could have some other information in a certificate, and you'll see some examples of what certificates look like. But for now, we can just think of it as very simple. It's just like, here's a subject, here's a public key, and it's signed by certificate authority. Okay, so this makes sense? Okay, does this actually solve the problem? Do we now know that the tunnel ends at google.ca? No, why not?
Because what if the user tried to make a proxy or whatever between him and Google in this case?
Yeah, okay, so the adversary's in the middle, so they could impersonate Google, right? So they could say, okay, I'm Google. I'm in the middle, so all the traffic going to Google I'm going to see anyway. And I'm going to put my public key in there so I can decrypt it in the middle. All right, so it's working so far. But now I need a certificate authority to sign my thing, right? And maybe I can't get that.
I'm not sure if there is a way to get the certificate authority signature, but sometimes it's doable. That's what I know.
Okay. So maybe we could attack the certificate authority somehow, and we could get the certificate authority to sign our key instead of Google. So that's reasonable. How does the user know? Okay, so they see it signed by the certificate authority. To verify that something's signed by a certificate authority, what do you need to know? Public key. So the public key of the certificate authority. Okay, so the reason that the tunnel ends at Google is actually because they're signing stuff. So they're going to sign some stuff in creating HTTPS, and they have this public key, and we got to know that that's really their public key. All right. How do I know the certificate authority's public key? If I validate this certificate, I need to know the public key of the certificate authority. Otherwise, I have no idea whether this certificate is right. Right? Okay, now aren't we just back where we started? I mean, this certificate is solving the problem of I don't need to know what Google's public key is because I have this certificate. That was the problem, right? Certificates are like a solution. But in order to trust the certificate, I have to know the certificate authority's public key.
Maybe it's hard-coded.
Okay, so we first off just recognize we went in a full circle. Okay, so the solution to knowing Google's public key required me to know someone else's public key. All right, so we got to solve that. Now, a second issue is, how did the certificate authority know that that was Google's public key?
Because Google made a application to the authority, and then it approved it.
Okay, so if the certificate authority, if Google's able to provide evidence that this is their public key to the certificate authority, why don't they just provide that evidence to us as users? Then we don't need certificate authorities at all, right? Somehow Google convinced the certificate authority that this was its correct public key. And it's easy to think about Google. They're a big company. Everyone knows Google, blah, 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 blah. You know, you walk into their offices and their IT staff, right? But this could be your website, okay? Some website that like 5 people visit, all right? How does my browser, Safari, on my Mac that I just bought at the Apple Store yesterday know that I'm talking to your actual real site, right? You're going to show me a certificate. Well, how did the certificate authority figure out that this is actually your real key? But what if the adversary was there on the very first connection? So that is called trust on first use. So there is some protocols where, like SSH is a good example, where you just hope that the first time you connect, it will just say, this is my key, and you hope you get the right one. And then you'll remember it forever, right? So that is one way of doing it. SSL's it's too important to do trust on first use. Okay, so let's write down these questions, and it's actually going to take a bit of time to answer both of them. All right, so the first issue is, how do you know that the certificate's public key, right? All right, so this is the same problem that we're trying to solve. How does Alice know Google's public key? If she can figure out what Google's public key is, she can figure out what the certificate authority's key is. But if she can figure out what the certificate authority's key is, you don't really need a certificate authority, because however she figured that out, she could use that mechanism to figure out Google's public key, okay? And then the related question is, Alice figures out the CA's true key, but the CA has to figure out Google's true key. Okay, so however the CA figured out Google's true key, the user could just do that. Alice could just do it, and then we don't need certificate authorities either. Okay. And why can't Alice just do the same thing? Then we can just get rid of CAs. Okay, so let's talk about issue 1 first. How do I know the certificate authority's key? And so the answer was actually already given. It's hard-coded in your browser. And the format that they're hard-coded, they're sometimes called root certificates. So it's basically a certificate that signs itself. So there's no signature on the root certificate because that would just be circular. So it's, anyway, so it's a certificate that's signed by itself. So it looks like a certificate as opposed to just a key. But theoretically, it could just be a key where there's some small distinctions that don't matter, okay? And so it's hard-coded. It's either in your operating system or your browser, depending on what exact software stack you're using. Or it's in both, to say it that way. So I go to the Apple Store. I buy a brand new MacBook, turn it on for the first time, never been connected to the internet. Even before I connect it to the internet, it's hard-coded. Certificate authorities are hard-coded in that computer, okay? So I'll show them to you in a second. Now, if I install some browsers, so for example, let's say I start using Safari. Safari will just it's made by Apple too, so they'll use the operating system. If I use Chrome on Apple, it will also just say, well, whatever Apple has in its operating system, that's the certificate authorities I'm using. If you use Firefox, they're like, well, we actually have our own certificate store. Okay, so when you download Firefox, it comes with a different set of CAs. There's a lot of overlap. Okay, like you could think that if a website was in one of the lists but not in the other, then it's not going to work for all users, and that would be bad. So essentially, there's almost full overlap. Or sometimes sites get a certificate from different certificate authorities just so that they cover all of the different browsers and operating systems. But anyway, so Firefox has its own set. So in that case, you'd use the browser instead of the operating system. And Windows is similar. I forget the exact details of it, but anyways, Microsoft definitely maintains a store. And then I think Firefox definitely uses their own. And I forget about Chrome on Windows, how it works. And then Linux would be similar as well. Okay. So anyway, someone's giving you a set of certificates. So let's say you're like me, you use an Apple computer and Safari. If you want to see your certificates, you can look them up. So they're in an application called Keychain. Keychain has all your passwords, like anything secure that you need stored, it will store for you. And it includes root certificates. So let me actually just take a screenshot of this first. Oops. So you can see if you're looking for it's under system roots, and then you have to click certificates, and then you'll see it. So let me paste this into the notes. Okay, so here they are. Now, the first thing that might strike you is there's a lot, right? I don't know what you were expecting. I was thinking maybe, I don't know, there'd be 3 or 4 or 5, right? There's hundreds, maybe not hundreds. I think there's 50 if you count them. Some of them are like from the same thing. So if you look, Amazon, for example, they have 4 root certificates altogether. Okay, so that might be the first thing that strikes you is that it seems like there's a lot. Okay, the second thing is, so Amazon, who's heard of Amazon? Okay, for the recording's sake, I'll say that everyone put their hand up, even though you're too shy to. Okay, how many people have heard of ANF Global Root? For the record, 0 hands went up. How about Affirm Trust? How about Audio Riyadh, Belgium Root, Bypass? Just put your hands out. Shout out if you've heard of some of these. Cert Plus, Certum, Komodo. Okay, so that one's infamous for reasons that aren't great. Intrust is actually a Canadian company. GeoTrust, Global Sign. GoDaddy's maybe one that you've heard of. But anyways, okay, the point is that a lot of these you haven't even heard of, okay? And you're implicitly trusting them. These are the people who are telling you when you connect to Google that you are actually connected to the right Google website. And so you should trust them, but they're not, there's some there that are global brands like Amazon and Apple, but there's a whole bunch there that you have no idea who they are, okay? Okay, so we have this sort of trust problem where normally in a security system, you want to kind of reduce your trust. If you have, let's say there's a safe and there's a combination and you tell that to one person, I have to attack that one person, okay? If 1,000 people know that combination, right, that's a little easier for me as an adversary because I can just attack one of them, okay? And so when you see a list of like 50 of these, security is based on this principle of the weakest link. Okay, so whatever the weakest link is in that list, if I can attack them, then this protocol has the property that if you can control any CA or just one CA, it can issue a certificate for any site on the internet. Okay, so it's not like if I want to attack Google, I have to attack one of these CAs. I can attack any of them. Okay. Now there's a bit of nuance around that now with projects like certificate transparency, but generally that's true. Okay. So any CA can sign a certificate for any site. And your browser will accept that certificate as being correct. Okay, so I would rather see a list of 3 companies than see a list of 50 companies. Okay, that's a much bigger attack surface area because now I have to worry about all 50 of these companies being secure. Okay, not allowing someone to breach them and issue certificates. But it gets worse. So with certificates, these are the so-called root certificates, but it turns out that there's other people that are allowed to create certificates for websites. These are called intermediary or subsidiary certificate authorities, and I'll show you how they work. Okay. So let's say there is a root certificate in my store, like the kind of thing that you just saw, okay? So the subject will be the name of a CA. It will have some key, whatever it is, blah, 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 blah. And then it's going to be signed by the CA itself. So the same, basically the same key that's here is the key that signs it. All right, so that's why it's a root certificate. And basically, it's no different than just saying this is the CA and this is the key. Okay, the fact that they sign it, they can throw some expiration information. There's a few reasons why you would sign it as opposed to just listing the key itself. But basically, the trust is the same as just publishing the key itself. Okay, so these are called self-signed certificates. Okay, and like we say, there's maybe 50 companies that have this kind of thing in an operating system, right? Now, what a root certificate can do is it can delegate its power as a certificate authority to someone else, okay? So they can say, here's another CA. We'll call it CA prime. And it has a key, whatever it is. And what they do is they put a little flag in the certificate that says, this certificate is saying that this isn't the key of a website, but this is a key of someone who can act as a certificate authority. Okay? So are they allowed to act as a certificate authority? And the answer is yes. Okay? And then it will be signed by the original CA. Okay, so the signature of this will be validated. Whoops. Okay, so you'll check that this thing was signed by this key. Okay, then what this certificate authority might be able to do, and there are some ways to constrain this. So there's a field here. This field right here is called basic constraints. And we'll come back to it later, but there's ways to stop this process from happening, you know, with 10 companies in a row or something like that. But what might be able to do, what this certificate authority might be authorized to do, is they might be able to further delegate to someone else, okay? So they can say, oh, there's this other person I know, CA double prime, and CA double prime, you know, they have this key, blah, 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 and they're allowed to be a CA as well, and I'm going to sign that myself. Okay, so this signature is signed by this person, all right? So you get certificate chain. Then this certificate authority might be the one that actually issues it for the site, right? So you have Google, and Google has whatever public key. We still don't know how it decided that this was the right public key. We'll answer that question later. And this will be signed by this second CA, CA double prime. Okay. So this is the website. We say that this certificate has a trusted path because it goes back to a root. So ultimately, this chain of certificates is signed by a root certificate. The whole thing is called a certificate chain. Okay, yep.
Why is there a need for an intermediate authority?
Sorry, why are there?
Why is there a need for it?
So it allows it. Let's just put it that way. So the protocol allows it for there to be intermediate certificate authorities. Ask me that question in about 2 minutes again. Okay. All right. So anyway, this is the state of it. So you have your root, and then these guys in the middle are subsidiaries or intermediates. Call them intermediaries. Okay. Now, the first question I want to ask you is, we said there's 50 companies that can issue a certificate for any site. That's because there's 50 root certificates. Is CA prime or CA double prime a root certificate? Okay, so they could be, right? But if they were, then they wouldn't have to do what you see on the screen, right? If they were a root certificate, then they could just start the chain at them, right? So if they're in the middle, then yes, they're almost entirely not a root certificate, okay? Sometimes an actual root certificate, they don't want to use their key, like they don't want to have it online signing a lot of certificates. So they'll first sign like an intermediate certificate, but it comes from the same company. And then they use that intermediate certificate to sign website certificates. So the root certificate might be like valid for 50 years. And then the intermediate is only valid for 5 years or something like that. So every 5 years they change their intermediate certificate. And then if I'm able to break in and steal the intermediate certificate, that's more vulnerable because they're using it a lot to sign websites. Okay, but the root certificate they can keep locked up and they only have to go and get it out of cold storage every 5 years or something like that. So sometimes for security reasons, actually almost like, I don't know of a CA that actually signs with their root certificate. Okay, so almost all of them will do this trick. And so that goes to your answer to your question of why these intermediaries exist. But sometimes it's actually a different company that's being authorized. Okay, so the root certificate decides that I trust, I don't know, the Department of Homeland Security of the US to be an intermediary certificate. And they'll issue a certificate that authorizes DHS to be an intermediary certificate. Okay, now how do we see, here's a question, how many intermediary certificates are there? How would I figure that number out? Where can I look it up? Okay, so I can look in the keychain with the list of signed certificates. Are the intermediaries listed in that set? They aren't. Okay, so that set is only root certificates. Okay, so where can I find the intermediaries? No. Basically, I can't. Okay, so they're out there, and you don't know they exist until you actually get a certificate from them. Okay, once you get a certificate from them, then you know, oh, hey, that person is an intermediary certificate. Okay, so we don't know how many there are for sure. There's like no list. And you basically they exist once you see them. Now, one thing you can do is you can go to every single website on the internet and you can write down the intermediary certificates that you see. Okay? This doesn't mean that you're going to get the complete set, because maybe that intermediary wasn't being used on that particular day, or maybe they saw the location that you were coming from and they show one certificate to people from this location, a different certificate to people from a different location. Okay? You could try and do that measurement from multiple locations around the globe, and people have done that. Okay, and when they do that, they realize that there's about, it depends how you count. So I've seen the low number is about 200 and the high number is about 600 of these CAs. All right, so that's from a measurement study of the whole internet. Now there's this new project called Certificate Transparency that's meant to log these certificates. And I'm not going to go into a lot of detail about it. But you can also look there to see the number of intermediary certificates. It's sort of a complicated story about whether an intermediary actually has to be in that database or not. And it's also a complicated story of what happens if you see a new certificate that's not in the log. And so it would take too long to explain it. But anyways, we're moving towards more transparency about getting these numbers. But the only canonical way to know for sure the number of intermediaries is basically to go to every website on the internet and then write them down. And then even then, you're not necessarily getting a full set. Okay, so now instead of having 50 companies, we have 600 companies. And so that's even worse from a security perspective because remember the key point, any CA can sign a certificate for any website. So that doesn't mean any root CA. Okay, that means any root CA or any intermediary CA. And generally, if you're CA double prime here, you might think, oh, the root certificate's more powerful because they're like kind of hard-coded, but they really aren't. Like there's not really much different. There's not really much that this person can do that this person can't do. This person might be able to issue new intermediaries. So by the time it reaches you, you might be able to only sign websites and not issue new CAs itself. So you might not be able to delegate further. That's one small difference. But in general, think of it from an attacker's perspective, if you can take over this CA, you're just as happy as taking over the root certificate. Okay. There's also like these revocation protocols. So it's hard to revoke a root certificate. It's still a mess, but kind of easier to revoke one of these. So there's minor differences, but anyway, in general, if you're an adversary, you don't care that you get an intermediary as opposed to a root. They're almost as good as each other. Okay, you can do a lot of damage with any one of these kinds of certificates. Okay, so security is based on the weakest link. So if you can breach any one of these CAs, whether it's a root or intermediary, then you can issue a certificate with your key for any site. So whatever key you know, you can say that's Google's key. You can sign it with your breached certificate authority. You can give that certificate when someone tries to connect to Google, and that person's browser is going to believe it because it's signed by a real certificate authority. It can trace that certificate authority back to its root store, and so it believes that it's actually talking to the real Google when it's really talking to the adversary. All right? So the attack would basically look like this. You would have to be in the middle, but we're considering that. So you would see that actually before you have a tunnel, you would basically also be like, okay, get cert for Google. The adversary's in the middle, so they see this happening. And so what they do is they go off to the side and they go over to their CA and they say, okay, someone wants to connect to Google, quick, give me a Google certificate, right? So the subject will say Google. The key will belong to the adversary and it will be signed by the CA. Okay, and then they'll return the fake certificate. It's fake in the sense that it's not Google's real key, but it's real in the sense that the browser will trust it. Okay, then what they could do is they could actually go to Google themselves and get the real certificate. Okay, and the reason they do that is when Alice starts sending traffic, Alice will create a tunnel to the adversary. The adversary sits in the middle. They can decrypt, and once it's decrypted, they can change. Okay, so they can modify and decrypt, and then they can actually forward that data onto the real server. So if the user asks, like, give me my homepage, like say it's Facebook, give me my like feed or whatever, then the adversary can get that user's real feed and then return it to the user so it looks like a real experience. It looks like they are actually interacting with the real website. But the adversary's in the middle, they're recording all of the information that they see. And if they want to change a few little things, they could do it, like change someone's message to them or whatever they want to do, they can do. Okay? So this is a classic man-in-the-middle attack where you're a proxy, you're relaying the information, but you're in the middle, you're decrypting everything, and you can do whatever you want in that kind of position. Now you don't have to do this. You could just reply with fake Facebook, like make it up yourselves, not get the information from real Facebook if you want. Like it's totally up to the adversary what they want to do. But generally what they'll do is they'll relay information back and forth. They're just in the middle and they're decrypting it all. Okay. All right, so any CA, you can breach it, you get their public key, and then you can issue a certificate for any site. There's another way to get basically the key or the certificate for any site. And let's say you're a government, you could actually go and you could legally compel the CA. You could say, okay, you're a CA, you're in Canada, I'm the Canadian government, I demand under security laws that you give me your public key so I can issue certificates, and then I could spy on all Canadians as the Canadian government. Okay, so when people realize this, security researchers, then they looked more politically at, okay, who's this list of CAs? Okay, where are they located? What countries are they located in? Is there any governments that we don't really trust based on where they're located? And if that government were to take over a site, even if, let's say it's not the Canadian government, some other government, and they were able to take over a CA in their country, that CA can still issue a site for, or a certificate for any site on the internet, and that certificate can be used to intercept any traffic from anywhere on the internet as well. So it could still impact me, right? Even though I'm sitting in Canada, I'm talking to a Canadian website, they would have to get in the middle of that connection somehow. But if they were able to get in the middle of the connection, it doesn't matter that it's a CA that's not from Canada. Okay. Then there was some like thought about whether you could limit CAs, so like you could only issue certificates from a CA that's located in the same country as you, and all those things like basically never materialized. And so anyways, so most people have gone through the list, and there's some concerns, I guess, about some of them. Like, for example, the Department of Homeland Security isn't a made-up example. So in the US, they're one website. There was a big furor over a telecom that's based in the UAE that some of you may have heard of. I don't know how to say exactly. Etisalat. I'm probably butchering it. But anyways, the reason that it was of concern is not because of something that happened in SSL, but something that happened in terms of smartphones in the country. So they're a telecom, and telecoms can give you a phone, and there's different ways you could get a phone. So like if I get a phone, like say I have an iPhone, right? And so this runs Apple's software, okay? I'm on Bell, but Bell doesn't put anything on this phone. This phone is just pure Apple's operating system. But Bell might sell you a phone where they actually put the software on it. So there's different versions of Android, and they'll customize it, and it will come with some like stuff that's baked into the operating system from Bell itself. So this telecom had done that, but they put some backdoors into the software. And then it was discovered that they did this, and then it looked like it was compelled by the government. And so then security people were really mad about it. And I believe they fixed the issue, and so the phones aren't backdoored anymore. But then someone realized, oh, hey, they have an intermediary certificate. And so they could do the same thing for SSL. And so there was a big push to kick them out of the certificate store, or kick out even the certificate authority that gave them the intermediary certificate. And I don't remember the outcome of it, whether they got kicked out or not. But I remember it happening. I'll have to look that up. But anyway, so this isn't just a completely made up example. This is something that could happen. Okay, now let's think about the second issue. So the first issue was, how do we know, let me just scroll back to it. How does Alice know the public key of the certificate authority to validate the signature on the certificate? And so the answer is they're hard-coded in the computer. And then we can answer the second question. So if we can hard-code Certicom's certificate into the browser, why can't we hard-code Google's or your websites into the browser? And the answer is sort of one of convenience and time. So it's a lot easier to encode 50 companies than it is to encode millions of companies that are on the internet. The second thing is that when I buy my computer, it comes with a certificate store that was created at the time I buy my computer. But you might have created your website after my software was updated on my computer. So my computer doesn't know about your website yet. Okay, so this allows that to still take place. So because it knows the CA, and the CA after I bought my computer issued you a certificate for your brand new website, I can trust your website even though my computer doesn't know anything about your website, right? It just knows that you have some certificate, and your certificate is from a certificate authority that I trust. Okay, so that's why we don't go hard coding every website into the browser. It's too much burden on the people who make like Apple and Microsoft. They can figure out, hey, these are 50 companies. We trust them reasonably. There's some guidelines and things like that they follow. How do you get to be one of those 50 companies? So a lot of these companies have been around for some time. But a lot of it's like just you sort of know the right people and you apply and you're big enough, and you know the sort of conglomerate of tech companies that control this list, they come to trust you enough, and then they'll add your name to it. So like Amazon wasn't in that list forever, and Google, I forget if they have a root certificate. They definitely have an intermediary certificate. They weren't in that list forever. And so this list sort of evolves over time, but there's no, like you couldn't just decide to be a CA and then show up and then they would say, okay, you can be a CA. There's still this human sort of review of you as a company and consideration and policies, and they might do an audit of you and try and figure out what your security looks like and things like that. So it's kind of a mess, but at the same time, it's still based a lot on human discretion, whether you get into this list or not. I'm really interested in that, and as security people, you should be interested in anything that involves human discretion, because there's usually ways of subverting that process. And so we're going to talk about that both in social engineering, and we'll talk about procedures, and I'll give you some examples, other examples of like basically things that, processes that involve humans deciding things that have security consequences. But anyways, that's a bit of a divergence for now. So let's turn our attention to the second question. How did the CA figure out Google's public key before signing the certificate? Okay, so Google showed up and they said, hey, I'm Google, here's my public key. And CA double prime somehow said, yes, you are Google. I believe that you're actually Google. I'm going to sign your certificate. Okay, so Google had to tell them something or convince them somehow. And then the other question you can think in your back of your mind is, whatever Google used to convince CA double prime that they got the right public key, why don't they just do that directly with every user? So whatever that evidence looks like, they could just send it to every user that connects to the website for the first time. Then we don't need all these certificate authorities. Then you can just get the key directly from the website itself. Okay, so let's think about how that works. So issue 2. How does the CA decide on what Google's public key is? Okay, so there's basically 2 ways. The first way is actually the way that you're maybe thinking in your mind, and maybe you're thinking, oh, this sounds too antiquated, it couldn't possibly be the answer, but it actually is, which is just old-fashioned in-person validation. Okay, so someone from Google will show up at the offices of whatever VeriSign, and they'll bring some documents with them, and they'll somehow convince them that they actually are from Google, and then they'll give them the public key, and they'll ask them to sign it. So it might be in person, or it might be like over mail, like not email. It could even be digital, but basically it's involving like real documents and things like that. I'll put phone here too. And usually if you opt for this, you try and get what's called an extended validated certificate, where you have the person's key, the certificate itself, so this is the certificate. All right, so the certificate will say like subject google.com. And then it will say, actually, this is like Google or ABC or whatever the parent company incorporated. It might say like Mountain View, California or whatever. Like this is the real business. Maybe it has the business number, so they're a registered business in the US, so they have some business number or something like that. So this is like the real Google, and this is their key. Okay, and so the certificate authority signs off on all of that information. Okay, so when you go, you know that you're not just talking to Google.com, you're talking to like Google, the company Google. Okay. Now the problem with this is it's expensive, it's slow. You can't get a certificate for days, weeks, right? There's a lot of paperwork that has to be sent back and forth. If you're some small company, it might be a lot more challenging. They might not believe you. And so what people said is, well, let's see if we can do some sort of fully automated process. Is there some way that robots or machines or servers can figure out that this is the right person without any humans having to be involved? Oh, by the way, this is called EV, which I should write extended. Okay, so it turns out that if you have a bunch of computers and they're trying to decide whether Google is Google, you can't get a bunch of computers to decide that this is Google, the company, in Mountain View, California. Like, it's too much knowledge. Computers can't handle it. Maybe with machine learning or something like that, they could maybe do it. But there's no way to know, like, there's no digital notion of what a company is and things like that, okay? So in the fully automated version, what we strive for is a little bit less. We strive to issue a certificate that just has the domain name. Okay, so it will say the subject is google.com. And this is the key. Okay, and so the key difference here is when I type in www.google.com, I get a certificate with a key, and I know that whoever's running that server, right, whoever registered the domain name google.com and put a server up and is responding, I have their true public key and my tunnel ends with them. But I don't know that that's the real Google. Okay, maybe someone else beat Google to that domain and got that domain name, right? So maybe it's not Google, the company. Maybe Google's at a different domain. Okay, and SSL is not going to break, or it's not going to say, oh, there's a certificate error because you ended up at the wrong Google. Okay, or let's say I mistype it and I put in Google with 3 O's. Whoever owns Google with 3 O's, they can have a certificate and they can have the lock appear because they are the legitimate owners of the domain Google with 3 O's. Okay, they won't be able to show me an EV certificate that says this is Google with 3 O's and this is Google, the Mountain View company. Okay, they won't be able to show me that because they aren't that company. Okay, but they can show me what's called a DV certificate, or domain validated certificate, because all that says is basically that, yeah, you got the right domain. You got the right key for the right domain. Okay. Now, when you go and you browse the internet using HTTPS, you see a lock. It doesn't matter if you get an EV certificate or a DV certificate. Okay, they both will close the lock and they'll both show you a lock. Okay, does anyone know how you tell the difference? Like, say I go to google.com. Let's just try it. Okay, so I'm looking. Here's google.com. If you click on the lock, you can go show certificate. Okay, you can see, this is actually just interesting for your interest. So there is GTS, which is, I believe, owned by Google. And so they have a root certificate and an intermediary, and then it was signed by Google. Is this like I'm talking to Google, the company, or is this like I'm just talking to whoever owns google.com? Okay, so no clear answer, right? No one knows for sure. If you looked in the certificate itself, you could read all the details of it, okay? And so you would see, there's a bunch of keys and stuff like that. And somewhere buried in this, I don't know if I can pull it out, but somewhere buried in all of this detail would be the answer to that question, okay? But it would be good if like users, like if you get an EV certificate, that's like better, right? It's like more trustworthy. Now you're more sure that you're connected to the right location. Okay, so it would be good if you could show users that, hey, this isn't just a lock. This is like an EV lock, right? I don't want to like click on all this and go through the details. Okay. Now let's try another website. Okay, that did not work the way I thought. Let's try Facebook. Now, I haven't tried this trick in a while, so I know Safari evolved in terms of how they do this. So let me just try another browser quickly. So this is another browser. This is based on Chrome. Sorry, when I screen share it, sometimes lags. Okay. I'm going to do some homework, and I'll show it to you next time. But anyways, I can show you how it used to work. So in the previous days, it might be that all of these use it or don't use it, and it might be the case that Safari just changed how they display this information. But in like 2 years ago when I taught the class, and for the longest time, there was an actual visual difference between them. And so the first thing is the color would change from gray to green. So if the lock and usually the URL was green, then you knew that you had an EV certificate as opposed to a normal certificate. Okay. Now the point I want to make is like almost no one knows that, right? They're just on a website, and there's actually a significant difference between getting an EV and a DV certificate. But like unless if you know, oh, a green means EV, right, and a gray doesn't, then there isn't much difference, right? Or that difference isn't communicated. There's a usability issue there where it doesn't matter because users can't tell the difference. The other thing they would do is in the URL bar, instead of displaying google.com, they would actually write, Google Inc. or Alphabet or whatever. Twitter, in previous years, Google didn't have a DV certificate and Twitter did. So when you view Twitter, instead of it up here saying twitter.com, the URL, it would actually say Twitter, the company. Okay, and sometimes they would have like kind of like both. So there would be kind of a green box, and it would say Twitter, the company, and then you would have the URL itself. That's how Chrome used to work. So, anyways, I clearly need to play around with this and do some research to see what the current status is. But I'll try and show you next class what the difference looks like if there still is a difference. I can show you a screenshot from the notes from last year so you can see at least what it used to look like. So previously, if you were on, like, say, a non-DV site, it would look like this. So you would just have a lock, and you would have google.com. And then if you went to an EV certificate site, you would see, for example, in Safari, it would be green. So it would be twitter.com, but it's in green now instead of gray. And on Chrome, you would see that it would display twitter.com, but it would also put Twitter Inc. US in a bar beside it. Okay, so that's how you knew it was an EV certificate. If it was just a DV certificate, it would just have the URL and not have this. It would have the lock and the URL, but it wouldn't have this extra information. So anyway, there used to be a distinction, and I'll report next class what the current status of things are. Okay, so let's start. The in-person one is pretty clear. There's not much you can do. The only thing that you could do is you could try to impersonate the website and have like fraudulent documents and things like that. So if you want to go to a certificate authority and claim that you are actually Google, you would have to impersonate the company. So you might use something called social engineering. We'll talk about that later. There'll be a couple lectures on social engineering. Has this ever happened? I'm not sure that it's happened with HTTPS certificates specifically, but another kind of system that uses certificate is software. So when you get like software, it's signed by a certificate. And so like say you're installing something on Apple and it's from Epic Games, then Epic Games will sign that binary, so you're not just installing random things, okay? And there are ways to install random things as well. But anyways, so that's called code signing. And there was a case of social engineering in code signing. So it actually was Microsoft that someone got a Microsoft certificate that for code signing that was issued to someone not from Microsoft, but they were an ex-employee of Microsoft. Okay, so it wasn't like a totally random person. It was someone I think they got fired, and then out of spite or whatever, they still had enough documentation that they were able to convince the certificate authority that they still worked at Microsoft, and then they were able to get the certificate. Then it was discovered and it was revoked. Okay, so this happened. With code signing and an ex-employee of Microsoft. So it's completely conceivable that this type of thing could happen with extended validation. Okay, what about domain validation? So there's a couple ways that you could fully automate this process, okay? Now, it's nice because you don't care like whether it's Google, the company, okay? So you don't care about the real world identity. Only the domain. Okay, so put yourselves in the shoes of a CA. So I'm a CA, and you come to me and you own concordia.ca. You come to me and you say, okay, I'm actually concordia.ca and this is my public key. All right. What I could do is first off, I could just go visit concordia.ca, right? And because you're coming to me for a certificate, I'm going to assume that you don't already have HTTPS. Okay, because you want to get a certificate, so you're probably wanting to turn HTTPS maybe for the first time. Maybe you're just coming to renew a certificate, but let's assume it's got to work in cases where you don't already have HTTPS, okay? But what I could do, it doesn't work very well, but what I could do is I could say, okay, if this is really your public key, I want you to put your public key on your domain at a specific location, like www.concordia.ca/public-key.text, okay, and then paste that text there. Then what I'm going to do is I'm going to go to your website, I'm going to browse to that text file, and if I see that public key there, I'm going to assume that that's actually your real public key, okay? So that would be like a kind of fully automated way of doing it. So that approach is actually used. And the problem with it is because that response, when the CA goes and asks for that web page, the response is coming back, but it's not coming back over HTTPS. Any adversary that's in the middle could modify that, so they could drop their own public key in. But this is slightly different than the original threat goal. So the original threat goal is we want to intercept Alice's communication with your website. But now I have to get in the middle of the CA and the website. Okay, so maybe that's a little harder. Okay. Then there's some other like tricks that you can do. And so I'll write these all out next class, but we're almost out of time. What I could do is I could send email to that domain. And so what I could do is I could say, okay, you really own concordia.ca. I'm going to send an email to admin@concordia.ca. And you have to know as a domain owner not to like give that email address out to anyone. That's a special email address. And I'm going to send an email and say, hey, I got this request for a certificate, and you said that your key is blah, blah, blah. Is that actually your key? Okay. And then then the person, the human that answers that email, they'll get that email, and then they can click, yeah, that's my actual public key, or no, that's not. Okay, I get that response by email, and now I believe that that's the actual email address. Okay, and so anyways, these are basically that's the essence of how this automated domain validation is going to work. Okay, but there's going to be some serious problems with it. So one is intercepting between. The other is like, how do I even find your domain name? So if I find your domain name, I have to go through DNS, and maybe there's some vulnerabilities on DNS. What if I hand out admin@concordia.ca to the wrong person? Then they have control of that email. Can they get a certificate for me? And so these are the questions you can at least think about before next class. Any questions on any of this? Okay, so we'll go through those details later.